What's that sound?
Not sure. Let me mute everybody. Am I recording? Do you guys see it? Yeah, it looks like I'm recording. Okay.
Alex?
Yes.
Why are there only 17 participants?
Because I guess not everybody has rejoined.
I just went out right now. My screen went out.
I guess we're waiting for people to join back.
Yeah, I had to disconnect everybody because of the 40-minute limit. And so we are rejoining for the third time. This is really unpleasant. I'm very disappointed.
Oh well, we tried to do everything for good reason, so it's
Yeah.
unfortunate, but we'll fix it. No worries.
You need to cancel annotation again.
Thank you. Disable attendee annotation.
You can also like enable. You can also turn on. You can see who's annotating.
Show names of annotators.
Yeah,
But I have disabled the annotations, so
yeah.
so now it's not going to work.
Find out who's
But
doing it then.
it's interesting that there is this feature, and it's kind of neat. So if I wanted to have you guys doodle on the slide, I could have you guys, draw, and everybody would be able to see it. But then we want the annotator's name to be recorded so that, everybody could then shame them if they make a mistake.
Yeah.
Okay.
Maybe
So,
you can see who it was in the recording.
It's okay. They can consider themselves shamed without us needing to do it proactively. So we were talking about real world problems. So we've got something like Facebook, okay, with millions of lines of code and thousands upon thousands of software developers working for them together on the same project. Now imagine thousands of people working on a software project that nobody has a complete understanding of. Everybody knows their piece, and they know something about the other pieces, but nobody knows everything about every piece. Indeed, nobody knows something about every piece, okay? What's the chance that somebody will make a mistake? I'm kind of implying that the chance that somebody is going to make a mistake is pretty high. So how do we deal with this?
Any ideas, people? How would you deal with this?
Maybe make sure that people can't have like so much power that their mistakes will mean a lot.
You can use a debugger.
Well, using a debugger on something like Facebook or Google, very large systems that thousands and thousands of people, millions of people are using at the same time, is not going to be a fun exercise. So yes, it's possible. If all else fails, somebody will have to use a debugger. But you want to have as much protection against bugs as possible. There is no, there's no silver bullet. There's a lot of things that need to be done. And if everybody does their job and does all of the things that they're supposed to do, then the chance of bugs is limited. And yet bugs happen nonetheless. So let's see what a few things that people do. Well, how do we know that code works? Testing. Now, traditionally, testing was done by a group of people called the QA engineers, quality assurance engineers. They would get a description of the software in English, and they would use the software, trying all the features of the software, clicking on every button, typing something in every text box, clicking on every link, and so on, trying to use every piece of the program. And they would make sure that whatever happened on their screen matched what the description said that the software should do. That worked up to a point, right? Simple systems display their state on the screen and enable a QA engineer, a quality engineer, to check everything that's happening. But complicated systems don't work that way. Complicated systems like, again, Google search, they don't really have a user interface. Yes, we do have a little bit of a user interface. I mean, we're seeing images of brisket recipes, but there's so much going on behind the scenes that needs to be checked and is not showing up on the screen. So you cannot check that Google search is behaving properly just by looking at the screen. You just can't. It's impossible. The information you need is just not there. So having a group of quality assurance engineers, though it's still important for some projects, it's definitely not good enough. So what do? People write unit tests. I personally think unit tests are somewhat overrated. There's a bit of a religion in Silicon Valley about unit tests. Unit tests are little pieces of code that invoke an API. For every piece of an API, for every method of an API, for every endpoint of an API, we write one test. Or we write one set of tests. So we say that we have an API that adds two numbers. And so we can call it with two inputs, A and B, okay? And ideally, both A and B have to be a number, right? If you give them two numbers, then if you give this API two numbers, it will give you back the value of the sum of those two numbers. That's the idea, right? So we would write a unit test that tries calling this API with two numbers that we know ahead of time what they are. For instance, it calls it with 1 and 2. And it checks that the result is 3, right? 1 plus 2 should be 3. And so we know that ahead of time, if we call that API with 1 and 2, we want the result to be 3. And so we do this with a bunch of different cases. We try to pay special attention to special cases. For instance, what if we don't do it right? What if instead of providing two numbers, we provide a number and a string? Well, what should the API do in that case? Well, it depends, right? But if we say that the API should only accept integers or only accept numbers, and we throw at it strings, it should not provide an answer. It should say, you gave me the wrong input. I can't do anything with it. So unit tests check both the good case where the API is being called correctly, and they check the wrong case where the API is being called incorrectly. And in all of these cases, the unit test checks that the API is doing whatever it's supposed to do. So that's important. And this is the first level of testing that we want to have. And at the very least, it ensures that in some cases the software works. That every piece of the software, at least in some cases, works. However, something like Google cannot be unit tested. Right? It's too big, it's too many pieces. So you want to write integration tests. Integration tests are kind of like unit tests, but instead of testing a single API in the absence of anything else, right? A single API disconnected from the rest of the world, they test complex pieces of software that may have many computers running, different services. A service is like a piece of software that runs on a server. So there's different services running on different computers talking to one another. We want to test that all of these services together do the right thing. And fundamentally, we're still writing the same kinds of things as unit tests, right? If we're, say that, our big system is the word count system that is able to count the number of words in very big files distributed over a large number of computers, we might run an integration test by giving word count 10 different files whose number of words we know ahead of time. For instance, we'd start with an empty file, a file that contains nothing. What should word count produce? It should produce 0 because there's no words in that file, and we know ahead of time that there's no words in that file. So we ask word count, what's the number of words in 0.txt? And we're expecting word count to do a very complicated thing on a million computers, at the end of which it produces 0. And we check that the result is 0. And if the result is 0, that test passes. And then we would check a bigger file, then a bigger file, then a bigger file. We do it 3 or 4 times. Now we've tested word count. Now, that doesn't prove that word count works in all possible cases, but again, it proves that there are some cases where word count, not a single piece of software, but the whole complicated software that runs on thousands of computers, works like we expect it to. So the combination of unit tests and integration tests goes a long way. Often, we also want to keep 2 copies or multiple copies of our software. We want to have a development copy that is available to the engineers that are building the software, but it's not available to the customers. And the developers can break things on the development server. And, if engineer John breaks the development server, engineer Jimmy will shame him publicly at the cooling machine, at the water cooler, or at the coffee machine. But beyond that, nobody really gets angry. So all of the tricky, risky work happens on the development server. Testing happens on the development server when the development server is rock solid and the unit test pass, the integration test pass, the QA engineers, if there are any, have done all their work and everything is fine. That's when the software is installed on the real production servers. The production servers are the ones that are used by the real users, the customers of the product. Okay? This is all very important stuff. Now, is this all? Is this all that you can do? No. And it's the beginning, but there's fancier techniques that give you some level of assurance that your software does something sensible even before you run it, even before you run any kind of test on it. And over the last 10 years, there has been a growing interest on the part of the software industry to use these other techniques, which are actually not new. They're pretty old. They are from the 1960s, really, and they're rooted in mathematical logic. But they have come to prominence in relatively recent times. These techniques are based on the idea that you can catch a lot of errors just by reading the code and making sure that it's doing something that, at least on the face of it, kind of makes sense. There's a lot of code that is syntactically correct, but in no way could it ever possibly work. It just doesn't make sense. Or maybe in some cases it might work, but in some other cases you can see that it would fail. Why? Because there's at least one part of the program that does not make sense. Maybe that part of the program is not being used, or at least not used frequently, but it doesn't make sense. So you don't want to have parts of your program that don't make sense. The techniques that allow you to check that the software makes some kind of sense even before you start running any kind of testing are called type checking. Java popularized strong type checking sometime in the 90s. So it's been quite a while. And even Java wasn't very strict about its type checking. It could allow a lot of mistakes to happen without the Java compiler noticing. There are programming languages that include far stricter, more powerful type checking. We've used JavaScript in this class. JavaScript is one of the languages that always try to do something with whatever code you write, right? We've tried adding an integer and a string. What happened? Do you remember? What happened was that the integer, the number, got converted to a string, and then the addition was performed on strings. And what does it mean in JavaScript to add two strings? Say that I want to add the string,
You guys remember we did that prompt and then we entered the number 3 and the number 4 and then we added them. What happened?
we got 34, right? We got 34 because we were really just gluing together the string that contained the word 3, or not the word, the character 3, and the string that contained the character 4. So gluing together a 3 and a 4 yields a 34, which is not the addition of 3 and 4, which should be 7. So JavaScript is a language that does not have static typing. It doesn't do any kind of type checking. It tries to do its best. And whenever there is a tricky situation and JavaScript tries to do its best, what ends up happening? A bug. Almost always. Almost always, if JavaScript is trying to step in and kind of interpret what you're saying in a way that could possibly make sense, it doesn't. It means that it's just wrong. So people have realized, because JavaScript is now possibly the most important programming language in the world, most of the software runs in a browser, and the software is written in JavaScript, you want to have static type checking. You want something to prevent you from doing something stupid like adding a number and a string, or adding two strings when you really thought you were adding numbers. So Microsoft has developed a new version of JavaScript called TypeScript. TypeScript is called type because it has type checking, which is really neat. It is also very neat because TypeScript translates into JavaScript. You write TypeScript, the TypeScript compiler can check that everything you've written could possibly make sense. It obviously can't check that it will do what you had in mind because it doesn't know what you had in mind, but at least it can check that it makes sense. There is some possible way of thinking about the problem such that your code would be the solution. It does this check, and then it strips away from the TypeScript everything that's specific to TypeScript, and it leaves just plain vanilla JavaScript. And you can take that plain vanilla JavaScript and run it in Chrome or run it in Firefox. Very smart. So type checking is, I would say, the most important thing that you can do as a software developer to ensure that the software that you write actually makes sense, is good, is free of very obvious bugs. So large projects, large software projects should be built using a language that supports static type checking, something like TypeScript if you're in the, if you're programming stuff that needs to run in a browser, stuff like Java, or languages that are even stricter than Java at type checking if you are writing software, something that needs to run on a server. So that deals with bugs. There's another problem that we have. The Google has, the Facebook has. They have thousands of engineers, and they are all working together, right, on the same project. That's complicated. Have you guys ever tried writing a team report? Somebody said what ends up happening is one guy does all the work, right? Realistically, right? It's so difficult to get 4 or 5 people to write a report together that in many cases in school, what really ends up happening is one guy ends up doing all the work. Now, in a good team, every team member would contribute something, but they don't necessarily contribute the report. They contribute a graph, they contribute the math, they contribute, an analysis, they contribute a prediction, a forecast, they contribute something, and then the writer of the report collects all the material and drafts the report. Now imagine a company like Google, I have no idea how many engineers they have. Let's say that they have 50,000 engineers. It's a wild guess. Maybe 50,000 is only the engineers they have here in Mountain View. 50,000 people. Can there be one guy who collects everybody's work and glues it together and produces the final draft?
What do you guys think? Is this feasible?
No.
Yeah.
Yeah? You're volunteering for
He's a robot.
You could maybe
I'm
use a
also
robot.
here.
You could maybe use a robot. That's actually kind of the direction that the world has really taken. There are tools that allow people to work together. And how do they allow people to work together? They really work by allowing people to not work together, to work independently. That's really how they work. Git is the most prominent version control system. A version control system is a system that maintains a group of files, most commonly text files, so files that contain letters and things that you can generate with your keyboard as opposed to images or videos. And these text files are program files. They're written in Java, they're written in JavaScript, they're written in C, C++, whatever other programming language you can think of. And Git, and possibly other version control systems, have the ability to maintain different copies of every file in different states. So how does that work? How does that enable many people to work together? Say that Sanjay and I are working on the same project. And I'm working on a file called, I don't know, a.javascript, a.js, and he's working on a file called b.js. We both have a copy of the Git repository. There is a current version of the software. He checks out the current version and starts making a change. I check out the current version, I start making a change. After Sanjay has made his change and I have made my change, we have two different versions of the project. My version contains my new feature, Sanjay's version contains his new feature. How do we glue them back together? Well, this is a case where Git really helps. Git has the ability to say, hey, these two versions are not conflicting. I can glue them together by taking Sanjay's changes and Alex's changes and creating a new copy of everything, a new copy of the entire project that contains both sets of changes. Clever, okay? Now, sometimes what happens is Sanjay and I are both making changes to the same file. Say that he's changing the top half of the file and I'm changing the bottom half of the file. This is also a case where Git gets even smarter. It says, oh, I realize that Sanjay's changes and Alex's changes do not overlap. I can still take Sanjay's changes and Alex's changes and inject them into a new version of that file such that it contains both Alex's and Sanjay's work. Super clever. Then there's yet another, even more complicated case that Git can't really deal with, right? It needs somebody's help. It's where I made a change to a piece of the file and Sanjay made a change to the same piece of the file. Now all Git can say is, look, you guys need to figure it out. I don't know. You both changed this piece of the file, right? I don't know who's right. You guys need to figure it out and tell me which of the two I need to use. That's called a conflict. Okay, there's a conflict between Sanjay's work and my work. There's no way that Git or anybody really could glue Sanjay's work and my work together and make sense of it. Because fundamentally we've changed the project in two ways that are not compatible with one another. Git picks up on that and says, guys, you have to deal with it. Tell me which version I need to keep, or if neither of the two is good, maybe you guys want to come up with a third version that you both agree with. Do that, and then tell me what to do. And so by allowing Sanjay to have his copy and work on his copy, and allowing me to have my copy and work on my copy, Git allows us both to be productive. Because we're, both Sanjay and I are working separately, and then we resolve our changes by merging them into the project. This is conceptually relatively easy. You can imagine sort of cutting and pasting Sanjay's work and my work into a common version, but there's a tremendous amount of intelligence that goes into writing the software that enables all of this to happen almost always automatically. The world would not be, as advanced as it is were it not for tools like Git. I mean, they're really a game changer for the technology industry. Now, some of you may have visited a website called GitHub. GitHub is a website that provides free storage for Git projects that are managed by Git. If the project is open source, in other words, if you are basically giving your code out to the whole wide world, you can use Git for free. If you want to keep your software, private, it's just yours, so you don't want to share it, then you have to pay GitHub to host the project for you. But GitHub is really just a place where you can store your files and make sure, have some other engineers make sure that your files will not be damaged or lost. Otherwise, you can just store your Git repository on your own computer. Okay, and then the green screen contest, we don't have access to, unfortunately. Otherwise, we could see what funny images Ms. Taylor's students have come up with. Questions? You guys still hear me?
Yeah,
Yeah.
absolutely.
Yeah.
And I'm realizing now that I went, 15 minutes past the allotted time. So thank you for your patience.
It's okay. We'll give them their money back later for that. It's okay.
Okay.
No, seriously, actually, Alex,
April
thank you
Fools.
so much. This has been awesome, guys. Hopefully, you understood the next step in. We kind of started this journey by talking about some basic computer science concepts. We built it all the way up to clients and servers, and now we're looking at how do you implement these huge systems that are spread across many thousands of computers. And so with these concepts, we'll now go deeper into some other things over the next few days. So anyway, guys, we'll not keep you any longer. So have a good night. And then Alex and I will discuss what are we doing about the next class.
Thank you.
You're welcome. Good night, guys.
Bye.
Okay, let me start.
Good night.
Good night, everyone. Good night.
Bye.
Bye.
Bye.